So this is on page 18 of your unit handout. We're dealing with satellite motion and Newton's laws of motion. I don't think this number is right. I think it's probably 3.10 maybe, or does it say 3.5? Oh, right, because it was 3.4 part 1, part 2, part 3, etc. So this is section 3.5 in your note package. And we're going to be solving problems that involve satellites. We're going to be using Newton's laws of motion and also using universal gravitation, which, to remind you, universal gravitation, thank you, universal gravitation, give me 1 second. Sorry about that. Universal gravitation is simply that the force due to gravity between two objects has a magnitude that can be found using the product of the masses multiplied by the universal gravitational constant divided by the distance from the center to center squared. The law of motion specifically that we're going to be using here in terms of Newton is F net equals ma. So we're solving satellite problems dealing with those two laws, the law of gravitation and Newton's second law of motion. Before we get started with the actual lesson, I think I need to make sure that you understand what a satellite is. A satellite is any object that is in an orbit around another object. So the moon is a satellite of the Earth. Any manufactured or human-made satellite that's launched into orbit is a satellite of Earth. Earth is a satellite of the sun. The sun is a satellite of the center of a galaxy. Neptune is a satellite of the sun. An electron is a satellite of a nucleus. Anything that's in some kind of orbit, swinging around another object, is a satellite. The difference between the moon being a satellite of the Earth, a communication satellite being the satellite of the Earth, Neptune being a satellite of the sun, Earth being a satellite of the sun, the difference between all of those and an electron being a satellite of a nucleus is all of those are in orbit because of gravity, whereas an electron is in a satellite orbit because of a different kind of force. And I mention that because I'm going to be using that terminology with you next year in Physics 30 when we talk about satellites in atoms. Electrons are satellites of nuclei. Okay. So in this lesson, we're going to be applying everything that we know about gravitation to satellites in planetary orbits. Although most natural satellites have orbits that are not perfectly circular, their eccentricity is negligible. And you might see that word eccentricity in your travels in high school physics. When you take a look at a circle, the eccentricity of a circle, there isn't any eccentricity. Okay? But if I take a circle and I make it into something that's not quite circular, and this could even be like that. I don't think that's circular. I think it's a little bit wider. Would you agree? You have to almost look at it dead on. So depending on where you are in the room, you might have to look at a different screen. The size of it doesn't matter. I'm talking about the ratio of the length and the width. And if we take a look at something like this, that's very eccentric. It has a high degree of eccentricity. Some planets have an orbit that's not a circle. It's called an ellipse. In fact, they are all elliptical. But the elliptical nature is very, very slim. It's almost circular. And if you use circular motion, the motion laws that we've been studying to analyze the orbits of planets, even though they're not in perfect circular orbits, it works. Okay? We could not really, with any confidence, use the stuff we're going to learn today to describe the orbit of the object on the right. We could use the physics that we're going to do today with the object on the right, but we would have to be talking about an average radius. And the radius is going to change over time. You don't really need to know that to be successful here. It's just that sooner or later I get high school students saying, well, I was told that the orbits of the planets are not circles. They're ellipses. Well, they're pretty close to circles. Some of them are more elliptical than others. I think Neptune is quite elliptical. So elliptical that I think Uranus and Neptune cross paths over the years. So sometimes one of those planets is further away from the sun than the other, and then they switch. And by the way, they never cross paths exactly because their lines of orbit are angled differently. So there's never a worry that they're going to bump into each other. So Isaac Newton had this idea that since we know objects with mass will accelerate towards the Earth due to the force of gravity, all objects will accelerate towards the Earth due to the force of gravity. Even the moon is accelerating towards the Earth due to the force of gravity. But it doesn't reach the Earth because it's falling around the Earth. This is a hard thing to visualize, and there's something called Newton's mountain that we're going to look at here. So what Isaac Newton did was he visualized the moon as falling towards the Earth, but due to the curvature of the Earth, it falls around the Earth. What does that mean? Well, if you imagine a mountain, that's a pretty big mountain. We don't have mountains that big on the Earth, but that's a diagram of the Earth, and on top is a mountain. And I take a cannonball, and I fire it at 2 kilometers per second horizontally off the top of that mountain. It's probably no surprise. It's probably no surprise that it hits the ground. Normally there's a little blink when it hits the ground, but for some reason it's not coming through. If I were to increase the speed to, say, 4 or 3.8 kilometers per second and fire it, it hits the ground further away from the mountain. And you can see that it's following a parabolic path. It's a curve. If I were to increase this to 20 kilometers per second, it's not coming back. If I were to increase it instead of to 20, maybe to 11, and I fire it, it's not coming back. It's not coming back because it's getting further and further and further away from the Earth. Now, with planetary orbits, it's possible for it to come back. It's possible for it to come back, but we're not going to worry about that. What about if we went to, I don't know, 5,600? Well, it's hitting the Earth, right? Let's try another one. Let's try 6,800. I think you see where this is going. We can maybe find some speed where it lands very, very close to the mountain on the other side. Let's try 8,300. Is it getting closer to the Earth? This one's going to come back, actually. And we don't get into the physics of elliptical orbits, but it will come back. See there? It's like throwing it up in the air and it comes back down. Just keep watching it. I think it's going to come back. Yep, there it is. And you might notice, again, this type of orbit we don't worry about, that it goes slower when it's further away. Oh, did it just go out? Oh, it hit him in the back of the head. That's what happened. But we want a circular orbit, so I'm going to decrease this a little bit. 6,800. Is it getting closer to the Earth? I did the exact same one?
Yeah.
Okay. So it's between 6 and 6,800? So what should I go to, Alex?
Go to
7,000?
7,000. Because it's like right at the halfway
It's close. A little more juice on that. This is not the... Looks like I can only go in increments of 100. Now it is getting a little closer, is it? It is getting a little closer, but then I think it's going to get a little further away. That's pretty close. Would 7,200 do it? And I don't know why I can't go at different increments, but let's try 7,200. And then we'll call it quits. This, I think, is getting a little closer, isn't it? I think it still might make it. But I would say 7,300 was pretty close. Okay. So, this is on page 18. What speed for the cannonball results in a fairly circular orbit? See, there I'm hedging my bets. I'm saying it's not exactly circular. It's fairly circular. And the answer was about 7,300. Was that what we landed on? So about 7,300 meters per second. What two possible things can happen? There's actually three possible things. No, I guess only two. What two possible things can happen if the speed of the cannonball is greater than the speed in A? So I'm going to clear this out. Let's go to 8,300. What can happen? And by the way, this isn't just some cartoon animation. It's predicting the path of that using the laws of physics. Why is it taking so long for it to move this distance at the bottom? Can anybody, while we're waiting for this to come back, oh, there it is. Why is it moving slower out here than it is over here? Excellent. It's less influenced by the gravitational pull of the Earth. There's less gravitational force when it's at this part of its orbit at the bottom of the screen because the force due to gravity drops off when the distance is bigger. Okay. So one possible thing that can happen is it can enter into an elliptical orbit. You can get an elliptical orbit. And I mean, we will study elliptical orbits a little bit, but the mathematics behind them is quite complicated. Everything okay there? Okay. What's another thing that can happen? Well, I think you know what the other thing that can happen is. It just doesn't come back. There's something called an escape velocity of a planet. So if it's at that magical speed, it completes a perfectly circular orbit. If it's less than that speed, it's going to hit the ground. If it's more than that speed, then one of two things will happen. It will enter into an elliptical orbit, or it will continue moving further away from the Earth. And by the way, that happens to be called a hyperbolic path. Okay. It can never return. I hate when you hear that on the news. Oh, when the astronauts have escaped the planet's gravity. No, they haven't. They're just really, really far away that they're not going to come back. Okay? Gravity's always there. So when a satellite, this is what we have to focus now on, is when a satellite is in a circular orbit. The net force acting on it is a gravitational force. I'm not sure that you really appreciate the idea of a vacuum, and I'm not talking, to clean your rugs at home. But when we say there's a vacuum of space, once you get a certain distance away from Earth and you get out of the atmosphere of the Earth, the atmosphere is a bunch of gases, including oxygen, but there's nitrogen and carbon dioxide and water vapor, that are gravitationally attracted to the Earth. That's why we have an atmosphere, is because gravity holds all of that air against the Earth. But once you get far enough away from the Earth, the atmosphere is no longer there. And when we say it's a vacuum of space, we mean literally, other than a few particles flying around, there's nothing there. There's no resistance, there's no wind, there's no air. If you're driving a car and you stick your hand out the window, you can feel the resistance. You can feel the friction pushing your hand in the opposite direction. If you were driving in space and you held your arm outside of your rocket, you're in a suit, so you're okay. It's not going to be whipped back by the wind. So what that means is when we have a satellite in orbit, there's only one force acting on it out there, gravity. And since that's the only force, that's the net force. But hang on a second here. If the gravitational force is the net unbalanced force, we don't need to say unbalanced. If the gravitational force is the force due to gravity, which is the net force, but it moves in a circle, then that net force is the centripetal force. And again, what I'm doing here is impressing on you the fact that I sometimes say F sub net and sometimes say FC. If it's moving in a circle, it's the same thing. This, everybody, is the key to solving all satellite problems where you have circular orbit. It's a physics idea that we're dealing with here. So, Earth's moon is that far away from Earth. Determine the orbital speed of the moon. That seems like an impossible task. But let's set it up. The net force acting on the moon is equal to the force due to gravity between the moon and the Earth. So centripetal force is the net force, which means ma. The force due to gravity is g times m1 times m2 over r squared. Now, question for you. Which m is on the left-hand side? I mean, you can call it 1 or 2. That's not what I'm getting at. It's the moon. I'm going to put m1, and I'm going to say m1 is the moon. Why is m1 the mass that we're multiplying by the acceleration? Why is it the moon's mass and not the Earth's mass?
Because we're trying to find the orbital speed of the moon. It's the one orbiting the Earth.
Right. It's the one orbiting the Earth, so it's the one experiencing a centripetal acceleration. So, by the way, I'm going to add that in now. I'm going to put a subscript for the acceleration and say it's centripetal. And the reason why, when you look at this problem, you go, well, I don't even know the mass of the moon. How can I answer it? You know what? The mass of the moon doesn't matter. Let's continue with our equation building. Let's not put in any numbers yet. Centripetal acceleration is v squared over r. So we end up with this. And I'm going to go ahead and put, I regret not labeling these masses to begin with, but I just wasn't thinking. M2 is the mass of the Earth. So now I have v squared over r equals g, mass of the Earth over r squared. Okay, well, I can cross multiply here. And what I'm going to get, sometimes I just have to have things just so, nice and lined up. I'm going to cross multiply, and top of the left side is v squared times bottom of the right is r squared equals top of the right is gm of the earth multiplied by the bottom of the left, which is r, and you can divide both sides by r to simplify it and get v squared times r equals g m of the earth. So all I've done is I've canceled an r from the left and the right, and that means v squared equals gm of the earth over r. Now, just a second. I think many of you are perfectly capable and fine with doing that. Because when you look at the top of the screen, one of these sides is over r, the other is over r squared. Why not just cancel an r there and then? And you'll be left with just a single r on the bottom of the right-hand side. So now the question becomes, what do we use for r? Well, you're told that the distance between the moon and the earth is that. Are we going to use that for r? I'm going to draw a picture. So we have the earth. I'm not an expert in astronomy, but I would say the moon has quite a tiny size physically compared to the earth. And what you are told is that the distance between the two is, what do we got here? 3.884 times 10 to the 5, which is 3.884 times 10 to the 8 kilometers. Sorry, meters. Meters. Because it was in kilometers. Would you agree? I'm just multiplying by 1,000. In Newton's universal law of gravitation and in circular motion, r is the distance from the center of the orbit to the object. So I technically have to add two things. I need to add the radius of the Earth and the radius, try that again, and the radius, I don't know if I can draw a line that small. Sure I can. And the radius of the moon. We don't know the radius of the moon, so what that is telling us, and I'm trying to teach you a little bit of problem solving and common sense strategy here, is the radius of the moon is not significant. If the radius of the moon were significant, then you would be told what it is. Do we know what the radius of the Earth is? So let's add the radius of the Earth to that distance and find out what we use for r. So we have 3.884 multiplied by 10 to the 8 plus, it's been a while, you should have your formula sheet out though so you can look at it, plus I believe 6.37 multiplied by 10 to the 6. Well, that is significant. It changes that number, doesn't it? So the radius of the moon is 1.7 times 10 to the 6. I guess we could add it in if we wanted to. But again, since we're not given that in the question, we can consider it to be insignificant. very often, just so you know before we finish this question, very often in a question it will say the radius of the moon's orbit is, and it will give you a number. If it tells you the radius of the moon's orbit is some number, that's r. You don't have to add anything. So let's get back to the question here. V squared will be equal to 6.67 multiplied by 10 to the 11. Yes, it has units of Newton meter squared per kilogram squared, but I'm going to leave that out to make the math easier to follow. The mass of the Earth, I can't remember, 5.98 or 5.97? 7. Thank you. All right, it used to be 5.98. Times 10 to the 24 kilograms, divided by that distance that we've calculated, which is 3.9477, times 10 to the 8. And we're not squaring that. There's no r squared here. We canceled one of those r's. So we have to calculate that and take the square root. And we'll get the orbital speed of the moon. We'll get how fast the moon is traveling in meters per second. You get the same answer? Are you stunned by that answer, or? A little bit. It's pretty fast, isn't it? It's a kilometer per second. But yet I go out at night and I look at the moon. I can't see it moving. I mean, if I look at the moon and then turn away for 10 minutes and I look back, it has moved. The reason why it doesn't seem like it's moving in the sky very fast is you just can't fathom that distance. That distance is so far away that, I'll do a calculation with you in a second, that distance is so far away that the orbit is so large, moving at a kilometer per second is not a big angular distance. So let's write down the answer here. V, after we take the square root, is about 1 times 10 to the 3 meters per second. Let's just for kicks, this is the calculation I'm talking about. Let's find the circumference of the orbit. This is not part of your lesson here, but circumference of an orbit is 2 pi r. 2 times pi times that 394770000. Thank you. $394770000. That's how many meters it is all the way around. So when you divide this by 1,000, this is how many kilometers it is all the way around, and it's moving at 1 kilometer per second. Well, it's moving 2,480,000th of its orbit in a second. You can hardly see it. All right, we have one more question that's a question of interest here with the moon. What is the orbital period of the moon? How long does it take the moon to go around once? We have an idea. It's about a month. It's about 28 days. But how can we find that? Well, now that we know the speed, we can use the formula for centripetal motion of speed equals 2 pi r over t. We can put in that 1,004 meters per second. We can put in that 984770000, and I'll double check that number. Pardon me, 394. $770000, and this is over t. So when you cross multiply that, t is going to be equal to, I'll just write it up here, 2 pi r over the speed. Two pi times 394770000 divided by that 1004.333. You don't need to carry all your decimals. I'm just being pedantic here, which means picky. I'll double check my numbers here. 2 pi r. R is 394770000 divided by the orbital speed will give me the orbital period in seconds. This is how many seconds it takes to go around once. Well, let's put that into perspective. I mean, you can write that number down if you like, but that's seconds. Divided by 60 will give me minutes. Divided by 60 again will give me hours. Divided by 24 hours gives me 28.6 days, which that's pretty close. Wow, they're saying 27 days. Who are you going to trust, Google or physics? 27 days, 7 hours, and 43 minutes. I'm wondering if, and I mean, I'm not blaming anybody, but I made this question. I'm wondering if that distance that they gave us was the actual orbit radius. And if we didn't add the radius of the Earth, I bet you we'd get closer to this. All right, any questions with the first example? All right. Landsat is an Earth imaging satellite, and it's got what's called a polar orbit. So the Earth is spinning like this. Right? It's spinning this way. But the satellite is in orbit this way. And as a result of that, it just continually takes pictures, and every time it gets to a new orbit, it's going to be imaging a new slice on the surface of the Earth. Because by the time it gets around to the next area, it will be moved over a bit. So it's a pretty ingenious method here. What do we got here? The height is only 912 kilometers above the surface of the Earth. How many of you have seen satellites at night? It's pretty cool because you'd just be stargazing, looking at the stars, and all of a sudden you go, hey, that star's moving. And it's not a plane. It's very obvious that it's quite far away. How many of you have seen the SpaceX satellites? Linking up. Every now and then you'll see them. It's a whole line of satellites. Like I've seen 5 or 6 at a time in the sky, and they're all moving. And then they disappear. And the reason they disappear is you're seeing them because sunlight is glancing off of them, but then they get to a different part behind the Earth, away from the sun, where you can't see them. What are the orbital speed and the period? Well, it's a satellite, so Fnet equals Fg. Could I have written Fc equals Fg? Sure. This is Ma equals G M over R squared. You'll see that what I'm starting to do, and I think it's a good kind of strategy, is in Newton's universal law of gravitation, I put little m and big M. And big M is the central body. Little m is the satellite. I can rewrite this now as Ma, this is AC, so mv squared over r equals G m over r squared. In case you haven't clued in, this is the exact same thing we did the first example. It's just not the moon, it's an artificial satellite. The masses of the satellite cancel. One of the r's cancel. And you're left with v squared equals g, mass of the Earth over r. So v equals root gm of the Earth over r. What are you going to use for r? Jay? Right. This diagram, by the way, is not, I don't believe, drawn to scale, but this distance from the center of the Earth to the surface is 6.37 times 10 to the 6 meters. This is 9.12 times 10 to the 5 meters, so it's not drawn to scale. All I did was I took 912 multiplied by 1,000 to get meters and then put it into scientific notation. So the total radius is this, and we have to add those numbers together. 6.37 times 10 to the 6 plus 9.12 times 10 to the 5 gives me 7.282 times 10 to the 6 meters. If you thought the moon was moving fast, wait till you get the answer here. These things move very, very fast, which is why you can see them moving across the sky. You notice it. So we're going to take Newton's universal law constant of 6.67 multiplied by 10 to the 11. Again, it has units, but quite frankly, we're just interested in an answer right now. That's your problem. If you're writing a written response assignment or quiz, that's your problem to put the units in there. You need to remember that. Times the mass of the Earth, 5.97 times 10 to the 24 kilograms over that distance of 7.282 times 10 to the 6. Of course, we have to do that and then take the square root. Just step back and double check my entries. I think they are okay. I hit equals. I need to take the square root. We're talking about 7.4 kilometers per second, which is, I mean, 1 kilometer per second is fast. But we can put this into perspective. The distance between Wetaskiwin and Millet is approximately, I'm just going to say approximately 15 kilometers. This is approximately 7.5 kilometers per second. So if you were traveling at this speed to Millet and back, it would take you 4 seconds. Take you 2 seconds to get to Millet, 2 seconds to get back. Go. 1,000, 2, 1,000. You're at the Petrocan in Millet. It's really fast. So 7.4 times 10 to the 3. Let's go meters per second here. You could write 7.4 kilometers per second. What's the orbital speed? What's the orbital period? Well, now what we can write is speed equals 2 pi r over t. Put in that radius, put in that speed, and find t. T will be 2 pi r over v. I'm just going to save a bit of time here and just do it all on my calculator. 2 pi times the 7.282 multiplied by 10 to the 6 divided by the speed, which is the number on my calculator. That's the length of time. I mean, it's moving fast, but it's going to take a little bit of time here. That's the time in seconds. If you divide by 60, this is the time in minutes. So, I mean, 103 minutes is starting to make sense in my head as to a length of time. It's less than one class, but it's kind of the same area. If I divide by 60 again, it's about 1.7 hours. Or I could have taken 103 and subtracted 60 and said it's 1 hour and 43 minutes. Any questions with that example? All right. Let's try to pick up the pace here. Use the mean distance of Mars from the sun and the mass of the sun. And I'm directing you to your textbook. This information is in your textbook, but you don't need to go there. I have it here. We want to determine the length of a Mars year. So if you were to find that table, Mars has an orbital radius, which is the distance between Mars and the sun. That's the orbital radius. So this time what we would do is say the net force on Mars equals, I mean the net force acting on the planet Mars. I don't mean the net force of you on Mars. The net force acting on Mars equals the force of gravity between Mars and the sun. So we would have m of Mars times the centripetal acceleration equals g m of Mars m of the sun over r squared. Gets a little bit tedious. We're doing the same thing over and over again. This becomes m v squared over r equals g m m over r squared. The mass of the orbiting body, which is Mars, cancels. One of the r's cancels. And I'm left with that for v. Help me out here, Alex. Are we asked to find the speed or the period?
Length of one Mars year.
Length of one Mars year. That's the period. That's how long it takes Mars to go around the sun. So you're going to calculate this. Then what you're going to do is calculate the time. So let's calculate the speed first. And you're going to be maybe a little bit shocked here. Maybe. I don't know. So I need to take Newton's universal constant of 6.67 multiplied by 10 to the negative 11. I need to multiply by the mass of the sun. Sun has a mass of, I believe, 2 times 10 to the 30 kilograms. 1.99 times 10 to the 30 kilograms. You would never be expected to memorize all of these. They would be given to you in the questions. So right at the top, I can see the mass of the sun. So I have to multiply by the mass of the sun. That mass of the sun is incomprehensible. I want to explain how incomprehensible it is in a little bit. And I divide by the orbital radius of the orbiting object, which is 2.28, multiplied by 10 to the 11. And then I take the square root. And it's going at 24 kilometers per second. And it's so far away. Like 10 to the 11 meters is so far away. Why is it still moving so fast? It's because the mass of the sun is, well, it's massive. The force of gravity is huge because of the enormous mass of the sun. So this is the speed. Let me drop this down here. This is the speed in meters per second. Now what we can do is calculate the period. 2 pi r over t equals v. Rearranged becomes t equals 2 pi r over v. And again, we've done, this is at least the third set of calculations like this, so I'm not writing this down. Hopefully you're getting the drift of what we're doing here. So now I go 2 times pi times the orbital radius, which was 2.28 times 10 to the 11, divided by that speed, 2 pi r over the speed, gives me that many seconds. I'll drop this here. You can write it down if you like, although it's not necessary. That's the period in seconds. If I divide by 60 to get it into minutes, well, my brain still can't cope with that. You know, oh, what time do you want to meet me? Come back here in 990,000 minutes. I don't know what I'm talking about here. So divide by 60 again. Still, that's hours. I don't know. Divide by 24 because there's 24 hours in a day. So the length of a year on Mars, the time it would take to go from one season back to that same season, is 687 days. If we want to, we can figure out how many Earth years that is by dividing by 365. 0.25 if you want to be picky, because we have leap years and it's not exactly 365, which gives me about 1.9 Earth years. Incidentally, I believe if you look at this table, it already has the orbital period in here, 687 days. It's not going to match exactly, because the constants we use, like the mass of the sun, it's not exactly 1.99 times 10 to the 30. Capital G is not exactly 6.67 times 10 to the negative 11. Let's do one more. How many of you have heard of a geostationary satellite? Look at the word, geo. Geo comes from the idea behind what Earth is. Geology is study of the Earth. Geostationary. So I don't have a satellite dish anymore. They're not very popular anymore because most people get their videos through other means. But you know, when I had an acreage, I had a satellite dish, and there's a satellite out there in orbit around the Earth, right? Well, if I want to watch a show, I don't hire somebody to keep turning that satellite dish to follow the satellite. The satellite dish pointed a little bit towards the south at an angle, and it stayed there. And what that meant was that if you had strong enough binoculars, or a telescope, I guess would be what you would use, if you pointed in that direction, you'd see the satellite there. And it would always be there. And what's happening is it's in an orbit around the Earth, around the equator of the Earth, and it's orbiting at the same rate that the Earth is spinning. So if the tip of this pencil is the satellite and the equator is a line here, what's happening is the Earth is turning and the satellite is rotating at the same time. It's not connected. Well, it's connected by gravity, right? So what that tells us is that geostationary satellites have to orbit with a period of 24 hours, because that's how long it takes the Earth to orbit once. Why would you want a geostationary satellite? Sometimes it's called geostationary, sometimes it's called geosynchronous. Well, the basic reason is whether you're talking about communication or global positioning satellites, they need to be above the same location on the surface of the Earth at all times. So I'm not going to write anything down here. You can come up with what you can add, or you don't even need to write it down as long as you understand the need for them. You know, your your GPS on your phone, or your GPS on my dash cam, which monitors my driving and how fast I'm going and all that, that GPS is continually connecting to a whole bunch of satellites that are always in the same place in the sky. If those satellites were in orbit, it wouldn't be very successful in trying to pin down my location, or it'd be more complicated anyway. All right, so at what altitude must you put a satellite so that it's geosynchronous? And this is going to open up all kinds of very interesting things that we can talk about. So if it's geosynchronous, the period is 24 hours. We already know that for satellites, we can set things up this way. MAC equals GMM over R squared. It's what, the 5th time we've written that today? And this becomes M times V squared over R equals G times MM over R squared. A couple of things happen. The mass of the satellite cancels, one of the radius cancels, and you're left with V squared equals G, mass of the Earth, over R. We're trying to find R, because if we know R, we know where the satellite is. So what we're missing is v. But v is 2 pi r over t. And now we have a problem. And I hate to break it to you, but all this stuff we've written is not helpful. We've painted ourselves into a corner because if you look at the bottom equation we developed, we want to find v so we can find r, but when you look up here, in order to find v, you need to know r. We're at a dead end. So this is the one very specific case where when you are here, you do not put v squared over r in for the acceleration. You put the other one. Was that what you were saying? Yeah. You put the other one. Normally, and I'll go back here and just show you, when we did this problem, the reason why this a became v squared over r is because on your formula sheet, it says centripetal acceleration is v squared over r. But it also says it's equal to something else. Look at your formula sheet. Is it 4 pi squared r over t squared? Okay, well, so that's what we're going to do here. We're going to say that it's m times the acceleration, which is 4 pi squared r over t squared. This equals gm m over r squared. And by the way, in any of the previous questions, when you were asked to find the period, you could have just done that and found the period from this formula. But I don't recommend it unless you have to use this formula. And the reason why is this. When you rearrange that formula for r, you're going to get an r cubed. The r's don't cancel. When you cross multiply, you get 4 pi squared. Let's be clear, the m's cancel. You get 4 pi squared, then you get an r cubed equals gm of the Earth t squared. Things are starting to kick it up a notch here. R cubed is g times the mass of the Earth times t squared over 4 pi squared. That's pretty powerful. You have the ability to find the altitude, or the orbital radius anyway, of a geostationary satellite, just using some physics 20. Of course, we have to use standard units. So this will be g, which is 6.67 times 10 to the negative 11, times the mass of the Earth, which is 5.97 times 10 to the 24, times 24 hours in seconds, which for some reason, and I don't know why, that fact is buried in my head, is 86,400 seconds. So take 24 times 3,600, which is the number of seconds in an hour, or take 24 times 60 times 60. But you get 86,400 over 4 pi squared. This is equal to r cubed. I want you to please follow along carefully up here because I have an important point to make. 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24 times 86,400 divided by 4 pi squared. Why is this going to give me the wrong answer? I mean, I'm not talking about the fact that I still have to cube root it. There's something else here. What's wrong with what I've entered? Jay?
You're dividing by 4 and then multiplying.
Right. What I've told the calculator to do is divide by 4 and then multiply by pi squared. What I have actually entered is g m I got to go back and look at this, is I've entered GM, and the other thing is, of course, I got to square that, don't I? So that's another issue. But what I've entered, I'm just going to assume that I did put squared here, is I've entered this. Without putting brackets around the 4 pi squared, it's wrong. And by the way, I do have to square the t as well. Okay, I forgot to do that. So I need to square the time. And then divide by, in brackets, 4 pi squared, or, you know me, I would probably go divided by 4 divided by pi squared. Okay. So there's GMT squared divided by 4 pi squared equals, now I have to take the cube root. The cube root function can be found in the math menu, and then you scroll down to the cube root of the answer. That's R, but that's not the answer to the question. This is the orbital radius of the satellite. So here's Earth. The number we just found is, what do we got? 1, 2, 3, 4, 5, 6, 7. 4.2 times 10 to the 7 meters. You're getting the same number, by the way? Okay. Why is that not the answer to the question?
It wants it from the surface.
Right, it's asking for the altitude, and altitude is how far from the surface of the Earth. So what you need to do is take that and subtract the radius of the Earth, and that will give you the altitude.